Well, welcome back, everyone. I'm very happy that we're going to have Professor Mark Davenport from Georgia Tech talk to us today. Professor Davenport is in the School of Electrical and Computer Engineering, and he is the winner of a couple of very prestigious fellowships, such as the Sloan Research Fellowship and the National Science Foundation Career Award. And his interests span a lot of interesting problems in signal processing with a focus on high dimensional statistics and machine learning. And I'm very much looking forward to this talk.
All right, thanks. So today I was going to talk about a couple of different problems related to matrix completion. And like Anna before me, I'm going to also kind of present some work by one of my students who is probably in the audience, who already presented part of this earlier this week. So I probably won't go into quite as much detail on that, but I'll include a little bit of it. So the big picture of the problem that I want to talk about today is matrix completion. So if you're not familiar with this idea, the idea is that we have some D1 by D2 matrix, and we get to observe only a subset of the entries of this matrix. And we're interested in basically recovering all of the entries that we didn't get to see. And the kinds of questions that people ask in matrix completion are things like, well, when is it possible to recover the original matrix? So obviously, if we have an arbitrary matrix, there's not much you can say. But if you have some kind of special structure, maybe it's possible. And then also, not just when is it possible, but how can we do this efficiently? How many samples will we need? Things like this. And so the matrix completion idea goes back a long time, but in, say, the last decade or so, there's been a lot of interest in a very particular framework for answering this question, which centers around the idea of low rank matrices. So just a matrix that has rank R, intuitively just means that it can be written as the outer product of these two skinny and fat matrices. And if you just sort of count the number of degrees of freedom here by looking at the SVD, what you learn is that, okay, well, this matrix has something like R times D1 plus R times D2 degrees of freedom. And this is way smaller than the number of entries in the matrix. And so the general idea in matrix completion is just that, okay, well, if there's fewer degrees of freedom than there are entries in the matrix, maybe we can subsample this matrix and not really lose any information. And there are a lot of cases where problems like this come up. I'm not going to delve into all of the details here. The classic example is related to recommendation systems. Used to be called the Netflix problem, but just the idea that you have a large matrix, say the rows correspond to users and the columns correspond to different items, and you get to see ratings from different users of some subset of items, but you certainly don't have any users that rate every item or any items that are rated by every user, and so you want to kind of infer how people would have reacted to some item they never provided a rating for. So that's one example that I'll probably come back to. But there are a bunch of other places where this idea comes up. And so there was a lot of attention, and we kind of have a good understanding of parts of this problem now. So I'll just give a very high level overview of what you can say. So if you have a D1 by D2 matrix M that has rank R, and you get little m samples on some set omega, so this is just an index set telling you where you're sampling, then you can recover m by solving, well, there are actually lots of algorithms. Maybe the simplest one to describe is a problem that says, okay, well, let's look at some problem where we try to minimize the error between our reconstruction X and our observations Y on the set omega that we have observed. So think of this matrix Y and X omega as just being the original matrix, but with zeros in all of the entries that we didn't observe. So we can say, let's minimize this error subject to, say, a nuclear norm constraint on X. And this nuclear norm constraint is, if you haven't seen this before, this is basically the L1 norm of the vector of singular values. And so this is encouraging kind of a sparse set of singular values, or to be low rank. And this is a nice convex optimization problem. There are efficient algorithms to solve this problem, and you can prove nice things about it. So in particular, you can show that basically, as long as the number of measurements that you get is basically the number of degrees of freedom in the matrix times some logarithmic oversampling penalty, you can actually recover the original matrix M exactly, as long as M satisfies certain nice properties that I don't want to get into. And there are also guarantees that extend this to the noisy setting. But what I want to talk about today are some problems that arise in practice that aren't really handled by the traditional matrix completion literature. So I'll just broadly call them problems related to quantization. So if you think back to these examples I was talking about, say like in the Netflix data set, the ratings you're getting are not real valued numbers. They're not real valued numbers subject to Gaussian noise either. They are integers between 1 and 5. You don't get to say that this movie was, you'd give this movie a rating of pi, no matter how much you'd like to do that. And in a bunch of the other examples, so anytime you're kind of dealing with, let's say broadly, anytime you're dealing with data that's being supplied by people, you end up often having them be very severely quantized, where people are just giving you, say, thumbs up, thumbs down, yes, no, agree, disagree. And also there are kind of a variety of other settings where maybe it's not quantized in the same sense, but you get the data that you're observing kind of naturally arises as some counting process. You could think of cases where you have imaging problems where the data you're getting actually corresponds to photon counts in different pixels, or topic models. This is an example I'll refer back to in a little bit. And I'd say the problem with all of these is that if you think about this kind of quantization, some of it quite extreme, this basically destroys low rank structures. So even if there's some nice low rank parameterization, once you force things to these kind of highly quantized scales, you really lose a lot of low rank properties. And I think this is kind of maybe clear what some of the problem is if I give an example. So this is an actual review that I found online for a book that a graduate student of mine wanted me to buy. So Naylor and Sell's linear operator theory book. And it had not very many reviews, but they were very good. So it had just a handful of reviews. And the top most useful review here is the one that says, I would give 6 stars, and then talks about how fantastic this book is. But it really actually highlights one of the problems here. So basically, if you only have 5 stars, then your true feeling may vastly exceed this scale, but you're not able to actually represent that in the data. So this is actually a big problem, and we decided to study this by looking at the most extreme version of it, which is to say, what if we take this matrix and we just quantize it to only 1 bit? So basically, think of some underlying matrix, and we just see the sign of some subset of entries. So we started working on this problem and then got very depressed and decided this was an impossible problem to work on, because there's a very simple example that makes it seem like things are hopeless. So suppose I have a matrix M that is just equal to lambda in every entry. So this matrix is rank 1, and it is also very incoherent. It satisfies all of the properties that you would want in matrix completion to sort of suggest that you don't need to sample it very many times to estimate the matrix. But I'm claiming that recovering M is impossible, because basically no matter how many samples you obtain, you don't really know anything about lambda except that it's positive or negative. And you can generalize this to other sort of simple rank 1 matrices and show that the error can be kind of arbitrarily bad. And that's true even if you know something about like the norm of M. So here you might say, oh, if we knew the norm of M, then we could, this wouldn't be as much of a problem, because if you know the norm of M, maybe you can say something about the magnitude of lambda, but even that is not enough to help you in general. But it turns out that once you get over being a little depressed about this and make the problem even harder, you realize that from another perspective, it is actually possible. So what happens if we introduce some noise? So imagine now, rather than just taking the sign of M, we take the sign of M plus some noise matrix Z, and Z has some distribution here. Well, it actually turns out that the fraction of positive and negative observations in this case tells you something about how big lambda is. So if you know the distribution of Z, you can actually say quite a lot about this underlying matrix M. This is somewhat reminiscent of the idea of dithering in stochastic resonance, if you've ever encountered these phenomena. We're taking kind of this sort of hard, sort of discrete problem and actually turning it into something that's a little bit more analog and getting more information out. So to be really concrete about what we're going to do here, we're going to have a probabilistic observation model where f of m tells us the probability we're going to see a 1. And this, if you think of f as being the CDF, this is the same model as what I was just describing. And so then we're going to assume that omega, the entries we get to see, are drawn uniformly at random. And we're going to do kind of a constrained maximum likelihood estimate. So this is the likelihood function that we're going to have. And we just say, let's maximize our log likelihood subject to some constraints on X. So we're going to have a nuclear norm constraint that's going to promote low rank structure. And then we're also going to have a constraint on the maximum entry of X. And I'll just go ahead and mention, we need this constraint for our theory. But when we actually run this algorithm, this constraint is basically never binding and does not appear to actually be truly necessary, but we need it in the theory. So what does our theory end up showing? So I'll give a very concrete example of this in the Gaussian case. So the case is, the result is to say, let's assume that basically we need some assumptions on M, and what they basically boil down to is that M is feasible in that it belongs to the feasible set, which will happen if M is exactly low rank, but it'll also hold for kind of approximately low rank M. And then we observe these kinds of observations, but where the noise is Gaussian. So that's what I mean by the Gaussian model here. And then we basically need to assume that we get enough observations, but this is the same kind of constraint that we saw before. And then what we show is that with high probability, the average Frobenius norm of our error is bounded by a constant times something really ugly that involves both alpha, which was the bound on the maximum entry in our signal, and so the maximum entry in the matrix, and on sigma, which has to do with the amount of noise that's being added before we take the 1-bit before we apply this 1-bit quantizer. So you have this really ugly term, and then we have something that's like the square root of the dimension divided by the number of, divided by m. So this is sort of an oversampling, a quantitative measurement of how much we're oversampling compared to the number of degrees of freedom. So this is a really ugly expression, but what we do is say, well, let's just, to kind of understand what would be possible, imagine we had control over sigma squared and could actually tune how much noise was added to get the tightest bound possible. And if you do that, so if you actually work through what's going to optimize things here, it turns out that the optimal bound will be achieved by setting sigma to be basically a very small constant times alpha, which is the maximum entry in the matrix. So if you do that, you get this much simpler bound. This whole constant basically reduces to some constant times alpha squared. And so this is, this suggests this is the best performance we're going to get. But that's a very strange thing if you think a little bit about what this constraint actually is saying. It's saying that we want to set the amount of noise we're going to add before we apply this sine function to actually be basically as big as the thing we're trying to estimate. But it turns out this is something we really observe in practice. So this really is going to be the best case scenario. So what happens is, this is just an example showing the relative reconstruction error as a function of log of sigma, so the variance that's being added to or the standard deviation of the noise that's being added. for a few different choices of rank. And so what we see is there really is this sweet spot where if the noise is very, very large, it's maybe not surprising that we just don't recover anything because our observations are just coin tosses. They're all just going to be plus or minus 1 because the noise dominates the signal there. But what's interesting is you do actually see performance degradation when the noise gets very small. But if you maybe think about this a little bit more, you realize that maybe that actually does make sense because in that regime, you're basically getting back to this noiseless case where you aren't getting this benefit of the dithering effects. So in this case, you have kind of poor performance. And then I'll mention we also kind of tried out this idea on sort of real world recommendation system data sets, and you do get kind of good performance with this approach in practice. But I think with my last few minutes, I want to talk about other directions. So what else can we do here? So you might think, okay, we've handled the 1-bit quantization case. Maybe we'll look at 2-bit matrix completion. It's actually pretty hard. We do not handle that. But there are a bunch of other people who've kind of taken up this work and talked about the general quantization case, but also sort of improved upon this analysis for other kinds of estimators that maybe enforce exact low rank constraints, or for other kind of weird noise models where this constrained maximum likelihood approach is useful. But then the one that I was really interested in and that Andrew McRae, my student, talked about earlier this week is what happens if you have Poisson noise. So this is a case where, basically our observations are Poisson random variables with some rate determined by this low rank matrix. And, it's very tempting to try to extend what we did before and say, well, let's just look at the log likelihood function and do some sort of MLE with structural constraints. And in fact, this was done by a colleague of mine at Georgia Tech, Yao Shea, and her student. And they got a result using kind of a similar analytical framework that we looked at. But the thing that I want to highlight is that it has this dependence on alpha squared, which is the same as what we were talking about before. It's kind of alpha is an upper bound on the entries in our matrix. But you also needed a lower bound on the entries in the matrix, this lower bound beta. And this is really unsatisfying because it should not really matter if there's one, if there's just a few matrix entries in your matrix that are very small, that shouldn't really bother us. There's no intuitive reason why this would cause problems. But if you look at what's happening here in this log likelihood function, the error basically the error blows up when, or the log likelihood function blows up when x gets small. And this causes big problems because this likelihood function is totally integral to the entire way we approach the analysis. And it's very hard to get kind of, our framework required getting a deviation bound on how much this log likelihood function could deviate from its expectation. But when it kind of blows up in this regime where things are small, you just can't get that kind of bound. So they had to make this assumption. And it's unsatisfying partly because one of the cases I was really interested in this model for is topic modeling, where you have a matrix, a low rank matrix that basically is telling you how common a particular word is in a particular document. And if you actually look at like real world data, what you basically, not surprisingly, find is there are lots of words that don't appear very often in many documents, but somehow we kind of know topic modeling already still works. So this is just a little unsatisfying. And so we looked at an alternative approach that my student Andrew talked about earlier this week. So I'll just very briefly say what we do. So we again look at a sort of a nuclear norm penalization, but then we completely ignore the likelihood function. We just throw that out the window and just say, so y star here just represents our Y matrix, our observations with zeros filled in on all of the entries we didn't observe. And we just say, let's just find some x such that when we compute the operator norm of this difference, that's small. And since we're dealing with Poisson data, we'll have a non-negativity constraint, and then we'll do nuclear norm minimization. So it turns out you can get an upper bound on this. Since I'm running out of time, I'm not gonna dwell too much on this. This is an informal statement as it is. But we can do some analysis here, and the kinds of terms we get are basically mostly the same, or log terms that we can often ignore. But then we have this term sigma squared here, or sigma tilde squared, which is just sort of a measure that depends on your matrix and tells you something about how much, how good of a matrix this is in this setting. And it kind of has a term that involves just sort of the underlying noise in the problem, but then this other term here that kind of is parameterized by how much sampling you do. And I think I have a very simple example of this where, what does this end up translating to in a simple case where we observe every entry. So if you observe every entry in the matrix and you don't impose any kind of structural constraints, you could just take the MLE, which is to just look at M hat being equal to our observations. And the expected Frobenius norm squared of your error is going to be just the sum of the entries in your matrix because of the Poisson noise. And what our bound says is that, okay, if you have to kind of think about this really ugly, complicated term, but it basically is a measure of how distributed the columns are, the energy in the columns are. And so if you have columns and rows that have comparable energy, then the bound you get is basically the same as what you had before, but with a factor out front that's R, the rank, divided by the bigger of the dimensions. And so this sort of, the error is controlled by basically how much you're kind of enforcing a low rank structure. So if you know it's very low rank, you get big improvements if the matrix is nice. This is somewhat like being incoherent. Okay, so let me just close. I'm already over time, so I'll make a few observations. So first of all, in talking about this Poisson reconstruction algorithm, I talked about this constrained nuclear norm minimization problem. It turns out that after we did all the analysis, we realized that you could remove the non-negativity constraint, and the theory is still true. So you can still get good bounds without the non-negativity constraint. And in that case, this algorithm boils down to take an SVD and do soft thresholding. And similar results are true for hard thresholding. And this, I think, is pretty surprising because we have kind of minimax optimality guarantees in this case. One caveat there is that that we sort of have optimality results, but they aren't imposing this kind of, they're not saying that for incoherent matrices we're optimal. And so I still think it's possible that you might be able to improve over this approach. And in particular, I still think that maximum likelihood estimates are a good idea. So they work in practice. We just don't know how to analyze them. And so I still think there's some open questions here. Going back to the quantized matrix completion case, if anyone's interested in this, I can talk about it more offline, but I still think there's room for improvement there too. So in particular, when the noise is small, there are things we don't quite understand. So I showed this result that things got worse when the noise was smaller. It turns out that if the rank gets bigger, they don't seem to get as bad, get quite as bad. So all my experiments were very low rank, but if the rank is like 10, somehow, even when the noise is very small, things still work, but we don't really completely understand why. And I would say, broadly speaking, these are both kind of reminiscent of gaps in kind of the broader noisy matrix completion literature, where we have kind of in parallel two bodies of work where on the one hand, people look at exact matrix completion results using dual certificates and kind of a very specialized kind of analysis, but they don't really give satisfying results in the noisy case. And then we have this more statistical estimation approach in the noisy case. But if you look at that literature and drive the noise to zero, you don't recover the kind of nice exact recovery guarantees. And I think kind of this regime where the noise is small is somehow just not completely well understood. So I'll wrap up there, and if there are questions, I can take them. I'll just briefly plug, if you're interested in learning more about matrix completion, you've never heard of it before, there's I'll say it's a nice review paper, mostly due to the efforts of my co-author from a few years ago. And if you're interested in learning more about one-bit matrix completion or this Poisson Poisson matrix completion, both of the papers are available on my website.
Thank you very much for your talk. Are there any questions from the audience?
I actually have a question, Mark. So you were saying that actually the likelihood method in practice for Poisson noise does work better, but your explanation earlier made me think it wouldn't because, well, I guess because if some entries were small, then that likelihood does get large, and the errors, you'd have to be much more precise. So when you say in practice, is it because usually in practice beta is positive, or if you put some zeros in the matrix?
So if there's zeros in the matrix, I think that's the one case we know how to handle. So if there's zeros in the matrix, you're actually okay, because remember, the thing that you're worried about is this likelihood function has this log of x, and as x gets very small, then log of x can kind of go off to negative infinity. But if the true matrix has a 0, then yij is guaranteed to be 0.
Right.
And so you can actually ignore those terms.
Okay.
The thing to worry about is, okay, well, what if there's just a very small entry, and then we get unlucky and we see something, and we have a yij is 1 on a very small entry, and so the algorithm is going to be trying to push xij, that corresponding x, to 0, but you're going to pay a big penalty for that.
I see.
But yeah, I don't know. That's my. I think it's. I don't know. I don't have a good answer for this. I'm not satisfied. Really.
But now I get a better understanding. So thank you.
Yeah.
Right. If there are no other questions, I would like to thank